as much. Therefore, we now generalize this whole thing and say that for a given wave, the time width and the frequency domain width will always be greater than or equal to a time bandwidth product. We have unambiguously established that using the effective width. What exactly this quantity is this theoretical minimum will depend on the definition of the width, but a pulse's time bandwidth product will always be greater than, or rather we can interpret it this way, every pulse, whether it is ideal, the best limited pulse or not, will have a TBP. This TBP will be limited by the theoretical minimum given by the uncertainty principle. Okay. And any pulse whose time bandwidth product is equal to the theoretical minimum is called a Fourier transform limited pulse or simply a transform limited pulse. The notion of a transform limited pulse. Now, how do we visualize this so called transform limit or transform limited pulse? So, here is the key to that. We have two quantities, delta omega and delta t. This is what we want to know, but cannot measure directly. This can measure easily, directly, and so on and so forth. Spectrometer would right away do this job. So, if I know delta omega, what about the delta t? So far all I know is that this should be greater than or equal to 2 pi if it is if I am using the effective width as a measure, right. But can I always say, hey, I measured delta omega, therefore delta omega is this, and so delta t must be 2 pi divided by delta omega. No, 2 pi can be greater than or equal to delta omega. Sorry, what am I saying 2 pi? Delta t can be greater than or equal to 2 pi divided by delta omega, or greater than or equal to 1 over delta nu. It is not always equal. The best, aka the shortest width for a pulse given a spectral content, a spectral width of delta omega, can be delta t shortest is equal to this 1 over delta nu if my definition is effective width. Otherwise, the 1 is replaced by something else. I use the effective width definition, then for a given delta omega, the best or the shortest width would be 1 over delta nu or 2 pi over delta omega. Okay, I hope I am not confusing nus and omegas, but you get the purport of what I am saying. The shortest width is equal to an inverse of the frequency content or the frequency spread. So, such a pulse is said to be transform limited. So, what are these transform unlimited or non-transform limited pulses? What are these guys? What are the non-transform limited pulses? These non-transform limited pulses are chirp pulses. A pulse with chirp 0, linear chirp 0, quadratic chirp 0, higher order chirp 0, and a pulse with a substantial higher order spectral content can both have a spectral content, because spectrum is only intensity. The S of omega of unchirped, linearly chirped, quadratically chirped, cubically chirped, quartically chirped, a pulse containing all these terms non-zero, phi 1, phi 2, phi 3, phi 4, phi 5, a pulse containing all these coefficients non-zero can both, versus a pulse with just non-zero phi naught only, which is unchirped, can all of these can have the same spectrum when measured. The spectrometer has no way to distinguish them. So, the non-transform limited pulses are chirped, whereas the best pulse in terms of the width is an unchirped pulse. If you now look back at the discussion we had on a Gaussian pulse carrying a linear chirp, we did. There, if you stick beta is equal to 0, the linear chirp coefficient to be 0, we immediately see that the width of the pulse comes down in the spatial domain for a given spectral width, and it falls into the transform limited case. So, now
all these defined widths are for the spectral intensity waves. Is there no way to find them for the carrier?
carrier is infinite. The envelope, you can have an envelope for the field or the intensity, it really does not matter. These two differ by factors like the square root of 2 and so on. Whereas the carrier wave is defined by its cycle period, which remains, which is for an unchirped pulse constant throughout. For a chirped pulse, this will change in time. We can determine the chirp of the pulse, but otherwise it is simply the cycle, the period of the wave, or the inverse of the cyclical frequency, or the reciprocal rather of the cyclical frequency. Okay, now in reality, lasers can emit pulses which are either close to a Gaussian, or it could be close to a secant hyperbolic or Lorentzian, or something asymmetric, which I am not sure how these are produced, even Lorentzian pulses, but these are all functions that come in either useful or are good descriptors in terms of describing pulses with analytical functions. Then all we need to have in our toolbox is this table, where if the field envelope is Gaussian, okay, that is the intensity profile, as compared to the half width at 1 over E point, which is T g. We would have the full width at half max, which is typically what we tend to measure. The ratios can be determined, the spectral profile can be determined, but then what should be the delta omega delta T product for each of these cases, the best or the theoretical minima are listed here for each of the pulse shapes. Okay. So, to get a measure of whether a pulse is transform limited, we would have to measure get not only a measure of the pulse width delta t, but also the shape of the envelope function. It's therefore pulse metrology is a full time job if you take it very seriously. Otherwise, as a practitioner, we can buy certain contraptions or build certain experimental setups or say devices which can help us determine this. We will come to that a little later. So, the time bandwidth product of a transform limited pulse with a Gaussian intensity and a constant phase has minimal TBP. Okay. So, this is something which one can demonstrate for oneself, say using a numerical program or something like that. We should always be mindful of the fact that there could be factors of 2 pi implicit in these definitions, because we use say omega instead of nu and so on and so forth. So, let us be aware of that. But a pulse with variable phase and variable intensity, this is also a legitimate pulse, though regular lasers do not emit such pulses when they work as they should. When they are working under the spec, they do not emit such a pulse. But then you see the frequency content can still be peaked at around the carrier frequency, whereas the phase profile can also be all over the place. You can still define, I mean this is the limitation of getting tempted to use the time bandwidth product of a pulse as a robust measure. Even a somewhat noisy pulse, I would say pulse which is not well behaved, it has sorry. This has 3 if not 4 major pulses within itself. Such a not so well behaved pulse can also have a small TBP, the way as we have measured here. The TBP of FWHM is 2.57. For a Gaussian, in fact, it can even turn out to be larger, right. But that is that. These are all artificial sort of, artificially short pulses. They are not well behaved. So, this is going to become a problem to address when we develop methods for pulse metrology. Okay, something to just keep in mind. Well, but then if you now turn the question around and ask, how will a pulse with a large TBP, maybe 100, look like? It is really like something coming out of the white light in this room, full of, it is just a spiky something. It is as if the pulse was turned on here, turned off here, and it was just a very fast blinking source, right. Absolutely, not worthy of being called a pulse maybe in some sense, but that is what it is. Okay. So, the point is that the time bandwidth product is therefore a measure of the complexity of the time structure of a pulse. Okay. Now, we can define another quantity called the coherence time Tc of the pulse, which is 1 over nu. Okay. We can compare this to the best pulse width we would have had, okay, which is the transform limited width of a transform limited pulse for a pulse with a spectral content of delta nu. Given a delta nu, 1 over delta nu is the best width or the shortest width we would have had for a transform limited pulse. Yeah. Now, in the case of a not so well behaved pulse, what does this quantity delta nu translate into? Now, in the case of this, what I may call a source with many broken pulses, with many peaky substructures or many spikes, this 1 over delta nu is called the coherence time. It is the width of the narrowest temporal structure that you can find. But we should not be surprised by this. If for any reason, right, a source produced this pulse, at every instant of time it is still limited by the constraint that delta nu delta t should be greater than or equal to 1. That is to say, if I consider just this piece of the source, I gated this out somehow, okay, do not ask me how. Suppose I had the means to do this, I simply cut this piece of the cake and then examined its spectrotemporal characteristics, right. Actually, the very act of cutting it would also introduce some spectral features and so on and so forth. That is, I multiplied this with some kind of a gating function in time, whatever I did. In electronics, multiplying two signals is not such a big challenge, right. That is low frequencies. How you do it in optics is another question altogether. But if I did this and now examined the delta nu delta t, then at every instant this uncertainty relation must be obeyed, or in other words, I moved this window around all the way from the left to the right. I moved around this window. A moving window transform, if I may call it. I put a window function and then do a transform and figure out, right. At every position of the window this must be true, and therefore, for a pulse with many spikes, Tc 1 over delta nu turns out to be the coherence time, which is the smallest structure that this pulse can have. Okay. So, a similar argument is also possible in the spectral domain, considering again the ratio of the spectral to the temporal widths. So, as I was mentioning earlier, a linearly chirped pulse is wider than a corresponding unchirped pulse with the same spectral intensity profile. We saw this earlier. Okay, now at least because I said so, I should jump into this, make a foray into nonlinear optics. We have only a little bit of time, so I will probably not elaborate things in great detail. In this subsequent section of the course, what we are going to see and do is the following. We are essentially going to ask ourselves the question as to what is the origin of refractive index, its real and imaginary parts, and then address the question of what is nonlinear about nonlinear optics, what does it lead us to, and so on and so forth. This is very pertinent for this course because nonlinear optics immediately means frequency conversion, going from omega to creating 2 omega out of omega, creating 3 omega out of omega, creating 4 omega out of omega, 5 omega out of omega. How far can I go? N omega out of omega. So, what we will first look at is low order harmonics being generated, or low order harmonic generation processes, whereas correspondingly there should be high order harmonic generation, or H, G for short. HHG is synonymous with attosecond pulse generation. HHG and attosecond pulse generation are the same. In this case, when the primary pulse is in the optical domain. Okay. So, therefore, it is only appropriate that we begin with low order harmonic generation. Okay. So, with that I will stop my lecture for today. We still have time for some questions, if there are any.